So, hello and welcome to a new lecture on statistics. The scope of today's lecture is to introduce the Poisson distribution. And we saw in previous videos that a distribution is basically a function that describes how many times a different outcome in a random experiment is obtained on average. And if we ask for the question how many times is this certain outcome obtained on average, then we saw actually that this question is closely related to what is the probability that this outcome is obtained in a particular random experiment. And today we are going to discuss the Poisson distribution. And here again it is a very special one. It is named after the French mathematician and physicist Siméon Poisson, who lived around the year 1700. And he's famous for many results in mathematics, statistics, and also physics and astronomy, etc. So what is a Poisson distribution, or when do we use the Poisson distribution to model a particular situation? So we have to understand that Poisson distribution can only be used to describe rare and random events, and it is usually used to describe unpredictable events that are monitored over a certain period of time. Typical examples are, for instance, car crashes on a particular highway section, or the presence of a formation of cyclones in the US Pacific, for instance. So let's write down a couple of properties. So the Poisson distribution is used to model rare and random events. The events, they must be unpredictable, and is used to monitor events over a certain period of time. And so the probability distribution, or the probability law of a Poisson distribution, is given by the following formula. So probability of a random variable to be x to be k, so k, the occurrence of k times the outcome we are interested in, for instance a car crash on the highway section, is given by the following relation: e to the power, so e to the power minus lambda times lambda to the power k divided by k factorial. And lambda is the famous Poisson parameter, and can be shown that this parameter is actually a positive number, so lambda being positive. And it can be shown, and I'm not going to show this in this video, but can be shown that it is equal to two of the main description parameters, namely the expected value. So the expected value E of x that I introduced in one of the previous lectures, and the variance of the distribution, which is also lambda. If you want me to prove this, I can do an additional video on this topic, but I'm not going to show this here. So let's do like in previous videos, let's work out a couple of examples for a certain parameter lambda, and let's choose lambda to be 3. So basically what we are interested in is p of x equals 0, so the event that the outcome is not obtained during this certain period of time. So what we then have is actually e to the power minus 3, so we chose lambda to be 3, times 3 to the power 0, because k is 0 and lambda is 3, and we have 0 factorial, which is 1. And if you actually do the math, you can easily work this out, and you will basically obtain, I mean this is 1 divided by 1 is still 1, multiplied by e to the power minus 3, which is e to the power minus 3, which is approximately 0.05. And you can do the same calculation for p of x being 1. basically what you obtain is again e to the power minus 3 times 3, but this time k is 1. So we have 1 here divided by 1 factorial. And if you do the math again, you basically obtain 3 times e to the power minus 3, which is approximately 0.15. Then you can repeat this calculation for p of x being 2, and you basically obtain approximately 0.225. And interestingly enough, for x equals 3, you also obtain approximately 0.225. And for p of x being 4, so that the event takes place 4 times, you approximately obtain 0.169. And for p of x, so random variable being 5, you approximately obtain 0.101. So with this, we are basically now ready to draw the probability mass function of this particular distribution. And here again, a probability mass function is represented on 2 axes on a plot with 2 axes. On the y-axis, you have the probability, and on the x-axis, you have the random variable. So here's the probability, and here's the random variable. So basically, we choose as random variables x equals 0, x equals 1, 2, 3, 4, and 5. And the highest probabilities are obtained for x equals 2 and x equals 3. So we are going to start with this, and let's say this is somewhere here, 0.225. So we have it for x equals 2. And approximately the same result for x equals 3. And then for x equals 1, we have 0.15. So 0.15 is almost in the middle somewhere here. So we are basically somewhere here. And for x equals 0, so we obtain this outcome 0 times, we have 0.05, so we are very close to the x-axis, so somewhere here. And then for x equals 4, we obtain 0.17 almost, so we are slightly higher than this result here. We are somewhere here. And for x equals 5, we obtain 0.1. basically, which means that we are slightly above the result of x equals 1, so we are somewhere here. And you could, of course, add additional random variables and the associated probability, but we are going to stop here. So basically what you see here is that you have a distribution, a Poisson-like distribution, which is not symmetric, of course. And this basically concludes the discussion on Poisson distributions. If you need additional information, or you want me to work out the statistics descriptive parameters, expected value and variance, please let me know in the comment section below. Like my video if you want more content like this, and subscribe to my channel if you don't want to miss videos in the future, and see you in the next video.